We're continuing section 6.1 on the basics of counting, looking at some more complicated counting problems. So already we've seen the product rule and also the sum rule. And so when you're counting up ways of doing things, you're often multiplying or adding. You might need a combination of those two. Also, we see subtraction. That operation is needed sometimes. Example 1. Suppose a password must be either 4 letters or 4 digits. So 26 English letters. There are 9 or 10 digits, 0 through 9. Okay, so if the password has to be 4 letters or 4 digits, how many possible passwords are there? A solution: let x be the number of 4-letter passwords, and let y be the number of 4-digit passwords. Well, we can figure out x using the product rule. And so the first letter, there are 26 options, 26 options for the second letter, third letter, fourth letter. So we need 26 to the power of 4 for x. And how about y? That's easier, so it's just 10 times 10 times 10. That's 10 to the 4, 10,000. And these are all the password options. So if you're a password, then you're either one of these X words or one of these Y numbers. So we need the sum rule here. We're not multiplying these. We have to add them to get all the possibilities. So it's this number plus this number. So what's that? 466,976. Okay, so I hope that made sense. So we're just adding the letter passwords to the number passwords to get the total. So this was a combination of the product rules, 2 product rules, and a sum rule. Okay, how about a different password example? So this time your password has to be 4 letters, and it must contain the letter Z. How many passwords are possible now with these restrictions? So we can think about it in 2 parts. So as we saw up here, if you're choosing 4 letters, then there are 26 to the power of 4 ways to do that. But the problem is, some of those passwords are not going to contain the letter Z. For example, the password ABCD. That's no good. It doesn't contain a Z, so that's we don't want to include that. We don't want to count that. So this 26 to the power 4, it overcounts by how many? So what are the bad passwords in here? Well, any password that does not contain a Z. So if it's made of 4 letters that are A through Y, then that's not what we want. Okay, so you can count the bad passwords. You've got 25 options for the first letter, 25 for the second. So the number of bad passwords is 25 to the power 4. Okay, so we take those away. So the number of good passwords is this difference, 66,351. Alright, so yeah, this is a common counting technique. So look at the whole set and then take away the things you don't want. So that's a subtraction. Yeah, so these good passwords, yeah, they have to contain the letter Z. I mean, they could contain more than one Z. But this way we're counting, we're getting what we want. Okay, example 3, subtraction can show up in a different way. Let's see, so suppose in a group of 100 people, 20 speak French, 40 speak Spanish, and 5 speak both languages. How many speak French or Spanish? And this is an inclusive or, it's how many speak French or Spanish or both. So is it just 20 plus 40 plus 5? Or is the 5 included in the 20 plus 40? So is the answer 60? Well, we have to be careful. Yeah, a nice way to think about it is graphically using these Venn diagrams. So we have our universe of 100 people. We can look at the subsets that speak French and that speak Spanish. We know there are 5 people that speak both, so they're in the overlap, in the intersection. 20 people in total speak French, so that means there must be 15 people over here that speak French but don't speak Spanish. And there must be, yeah, there's 40 people speak Spanish, 5 are here, so there's another 35 that speak Spanish and not French. Okay, so yeah, now it's clear. We can see, yeah, the total that speak French or Spanish or both is the sum of these. So 55. Yeah, that also tells us there's 45 people outside those two sets that don't speak either language. All right, so the answer is 55. But there is maybe an easier way to do this question using a general principle. So if you have two sets, we'll call them F and S. So the cardinality, the number of elements in the union, is equal to the number of elements in each set minus the number of elements in the intersection. So yeah, we saw that before. If you just count the number of elements in each set, then you're counting the elements in the overlap twice. So subtract the number of elements in the overlap just to get these intersection guys once. So we have this nice formula. Yeah, it works for any two sets. Okay, so the number of people that speak French or Spanish, that's the union. It's equal to the number of people that speak French, that speak Spanish, minus the intersection, that's 5. So we're just using these numbers. Okay, so yeah, we get the same answer, 55, in a slightly different way. And yeah, we're using subtraction again, this time subtracting the number of elements in the intersection. And this is a famous principle, the inclusion-exclusion principle. Okay, yeah, so you're including elements, but yeah, you want to exclude. Don't count elements twice. So that subtraction, yeah, it's in this context, counting context, it's the subtraction rule. Okay, so if you have a task that can be done in X ways or Y ways, but Z of those ways are really the same, then there are X plus Y minus Z ways to do the task. So yeah, so this kind of generalizes the sum rule. So for the sum rule, there's no, these X ways are all different from these Y ways, so Z is 0. So you don't have to subtract anything. So this is just a bit more general. Okay, yeah, so we didn't really have a task here, but you can see it's the same idea. And yeah, really we're just trying to find how many elements are in a set in the union. So here's a good example. Number 4, how many bit strings of length 8 either start with a 1, okay, so start with a 1 bit, or end with 0, 0, 2 0 bits. Okay, we can set this up with the subtraction rule. So let X be the number of bit strings of length 8 that start with a 1. Let Y be the number ending in 0, 0. Let Z be the number doing both. Okay, so can we count these? Okay, so how many bit strings of length 8 start with a 1? Oh, well, yeah, no choice for the first bit, but 2 choices for the second, 2 for the third, 2 So we get 2 to the 7 ways. So x is 2 to the 7. For y, yeah, the last two are zeros, so we don't need to. We don't have any choice there, but but we do have 6 choices. Yeah, this doesn't have to be 1. It could be a 0. So yeah, we have 2 choices, times 2 times 2. So 2 to the 6 ways. So y is 2 to the 6, 64. And for z, how many bit strings start with a 1 and end in 0, 0? So now this is a 1. And these are 2 zeros, so we only have 5 choices. So 2 possible bits here, times 2 times 2. Alright, so z is 2 to the 5. Okay, so this is a subtraction rule, so we're counting these bits. Okay, so we want bit strings either starting with a 1, there are x ways that can happen, or ending with a 0, 0, there are y ways that can happen. But there's an overlap between these two. There are z ways they can both happen. So we have to subtract those z ways. Okay, so it's 128 plus 64 minus 32. Okay, so 160 of these bit strings. Alright, so that's the subtraction rule. And yeah, it's definitely good to keep this picture in mind. So the z is counting the number of elements in the intersection. Okay, example 5. How many numbers between 1 and 100 are divisible by 3 or 5? Yeah, this is just another way of saying how many numbers between 1 and 100 does 3 divide or 5 divide. Yeah, so trying to set it up the same way. So we have this kind of 2 conditions. Let x be the number of integers that 3 divides. Let y be the number that 5 divides. And let z be the number that 3 and 5 both divide. Okay, yeah, so you can see, for example, 15 satisfies 3 divides 15 and 5 divides 15. So the numbers between 1 and 100 that 3 divides, so those are just the multiples of 3 in that range. So 3 up to 99, that's 33 times 3. Alright, so there are 33 of these numbers. So x is 33. How many of the numbers up to 100 does 5 divide? Well, those are the multiples of 5 in that range. There are 20 of those, so y is 20. And how many numbers does 3 and 5 divide? Well, those are the multiples of 15. And there are 6 of those less than 100. Yeah, up to 90. All right, so we have x plus y minus z in this case is 47. So 47 numbers from 1 to 100 are divisible by 3 or 5. So again, we counted the number divisible by 3. We counted the number divisible by 5. We're in this more complicated situation where there can be numbers divisible by 3 and 5. So we counted those. And using the inclusion-exclusion principle, or the subtraction rule, it's the sum minus the intersection. Okay, example 6, another counting integers question. This time we're looking at the integers from 1,000 to 9,999. How many of the integers in this range have distinct digits? So again, the digits, those are the symbols 0 through 9. And we want to count the numbers in here that have distinct digits, so no digit repeated. So this for this we don't need the inclusion-exclusion principle. We just need the product rule. So we can think of our first task is deciding what the first digit should be. So the digit on the left. Okay, it can't be 0. So it has to be 1 through 9. So there are nine options. So 9 ways to do the first task. And for the next digit, I have to be careful. So now 0 is an option, 0 through 9, but we have to exclude the first choice. So if we chose let's say a 7 for the first digit, then the next one is 0 through 9, but not 7. We want the digits to be distinct. So there are 9 choices for the second guy. Maybe it's a 4. For the next guy, now we're down to 8. So we can't use 7, we can't use 4, for example. It could be a 0. And then 7. There are 7 digits left for the last guy. Maybe 3. Alright, so by the product rule, it's 9 times 9 times 8 times 7. So 4,536 numbers in this range have distinct digits. So you can see there's about 9,000 numbers here, so about half of them have distinct digits. Okay, and the last topic in this section, tree diagrams. So yeah, we can't use the product rule if the number of ways to do the second task changes, if it depends on how you did the first task. So yeah, this more complicated situation, it's tougher to deal with, but yeah, we can use a tree diagram to try and keep everything straight. So just a simple example of that. How many integers between 20 and 49 have their right digit less than their left digit? Okay, so right digit less than their left digit. So for example, something like 31, so the right digit is less than the left digit. 1 is less than 3. We're looking for numbers between 20 and 49. Something like 27, that's no good. The right digit is more than the left digit. Even 22 is no good. We want it to be less than. Okay, so here's the tree we want. So yeah, this kind of shape is called a tree. Yeah, it's like an upside down tree. So here's the starting point, and so the first task is to choose the first digit. So the digit on the left, well, you can see the numbers we want, they're between 20 and 49, so the left digit, there are 3 options, 2, 3, or 4. Okay, so now it's, depending on which digit we choose, then there are different numbers of possibilities for the second task, for choosing the right digit. So if the first digit is a 2, then the right digit can only be 0 or 1. It can't be 2 or anything higher. If we chose a 3 for the first digit on the left, then there are 3 options, 0, 1, or 2. Or for a 4, 0 through 3 are all good options. Okay, so you can see for the second task, it's not the same number of options, not the same number of ways to do the second task. So that's why we can't just multiply, use the product rule. Okay, so for example, going this way, so 2 for the left and 0 for the right, so we get 20. That's a good option. We're starting here, 2 and a 1, 21. Okay, so you can see there are 9 dots on this row. Those are the 9 numbers that we're looking for. Going this way, that's 4 for the left and 3 for the right, so 43. Alright, so this kind of tree structure is very useful. Yeah, we used it when we were factoring in section 4.3. So the answer here is 9 ways. Or there are 9 integers with this property. Yeah, so these are the more complex counting problems. Yeah, internet addresses. Yeah, this is the inclusion-exclusion principle, the main formula. Yeah, we'll come back to this division rule. Yes, there is a rule for every operation. Let's see here. Yes, so example 21. So just to do one more tree diagram. How many bit strings of length 4 do not have two consecutive ones? Yeah, so this, yeah, you can think of 4 tasks. So the first task is to choose the first bit on the left. It's a 0 or a 1. But then for the second bit, we don't just have 2 options, 0 or 1, because if you chose a 1 for the first bit, then the second bit has to be a 0. We don't want to have 2 1s together. Okay, so we can't just use the product rule, 2 times 2 times 2 times 2, because of this condition is messing that up. Okay, so we can let's make a tree. Here is the tree. Let's make it visible. All right, so here's the starting point. Yeah, for the first bit, yeah, we can choose. So that can be a 1 or a 0, no problem. But then, yeah, like I was saying, if this is a 1, then the second bit has to be 0, or else we've got 2 consecutive 1s we don't want. If the first bit is a 0, then yeah, there are 2 good options, 1 or 0. If the second bit is 0, then yeah, we can have a 1 or a 0 next. But then if this is a 1, we can only have a 0 for the fourth bit. Okay, here it can be a 1 or a 0. Alright, so you can see we're just making sure that we don't have 2 1s together. And so in this situation, if the third bit is a 1, then the fourth bit has to be a 0. Alright, so now there are 8 dots on the bottom row. So that means there are 8 bit strings of length 4 that satisfy the condition. So no 2 1s, no consecutive 1s. Yeah, so for example here, going this way, we get a 1 0 1 0. Okay, that's this guy. So yeah, so no 2 consecutive 1s here. So that's a good bit string. And here are the other possibilities. Yeah, going this way, it's all 0s. That's fine. Okay, yeah, so these tree diagrams, that's a useful way to kind of systematically go through possibilities, as long as it's not too complicated. Alright, so that covers that section, yeah, basic counting techniques.